We're going to finish up stoichiometry today, and what you see today is not like anything you saw in honors. It takes it to a higher level. We're going to be doing advanced stoichiometry, and the stoichiometry chapter fits into big idea 1. In chemistry this year, we're going to be talking about 6 big ideas. Big idea 1 on the screen is linked to stoichiometry. So we're going to be looking primarily at how we can convert the mass of a compound to the mass of an element to the percent of an element, the empirical and molecular formula. It's going to look crazy. As we work through the problems, I'm going to write it out. I'm going to point some key things out to you. If you are having difficulty copying the problem as we go and you want to just watch, on Edline I already have it posted, and I can also post my work from today out if you think it's better than what's posted. So don't worry about scribbling everything down. I would focus more on understanding it. And you're going to work through a lot of the problems. You'll see it's only the first component that's new. The rest of it you already know how to do. So what we're going to be looking at today from your summer assignment is the advanced stoichiometry piece, and I had indicated that we would work out these problems together because it's a little more involved than anything you've seen before. We're going to work on the first problem and then the second problem. And your next quiz, which is next week, part 2 will be a problem similar to one of these. It's actually more like number 2 than number 1. Number 1's a little simpler, but it'll help us get going on the concept. So in this problem, you have a 0.1204 gram sample of a carboxylic acid. And that carboxylic acid is going to be comprised of carbon, hydrogen, and oxygen. Some of you will remember from last year the COO group. Carboxylic acids have that COOH grouping. It's combusted. If it's combusted, what does it react with? Oxygen gas. And you're going to yield 0.2147 grams of carbon dioxide and 0.0884 grams of water. You want to determine the percent comp and the empirical formula. Let's take a look at how to work this problem. I'll show you how I set it up so I can clearly see what's given, what I want to know, etc. Now this is a lot to write out, so on my paper I'm going to go landscape, and that's why I said for those of you trying to write teeny weeny in those summer assignment packets, I think you're going to be squished. In this problem we have some carboxylic acid, which I'm going to represent CXHY OZ. And typically you go XYZ on an empirical formula. If you have 4 elements, you go WXYZ. Some people do ABCD. Whatever rocks your world is fine. You're going to react it with oxygen gas. When you have a hydrocarbon reacting with oxygen gas, your products are always CO2 and water. And if you have an oxygen derivative of that hydrocarbon, you're still going to have CO2 and water. If you have a nitrogen or sulfur derivative, you're going to have another product here where the nitrogen or sulfur winds up in. I'll show you that in the next example. Our goal will be to figure out the empirical formula of this carboxylic acid. The sample we are given is 0.1204 grams. And from that sample, we're going to yield 0.2147 grams of CO2 and 0.0884 grams of water. So that's the information given. looking at the two product, which element is found in both products? Oxygen. We don't want to start with oxygen. It'll be tricky. From the CO2, I can figure out the mass and the percent of carbon. From the water, I can figure out the mass and percent of hydrogen. What we're going to do is we're going to use the mass of the carbon dioxide and in a multi-step process, I'm going to determine the percent of carbon. So what I'm looking at here is 1 mole of CO2 is equal to its mass in grams off the periodic table. So the molecular mass of CO2 there. Here's the new piece of the puzzle. And we started to mention this the other day, and here you'll see the importance of it. The example we gave in class the other day was for propane. And we said for every 1 mole of propane, you would have 3 moles of carbon and 8 moles of hydrogen based on the coefficient, or in this case, based on the subscript. The mole ratio allows us to convert from one substance to another. The mole ratio is the only way you can compare two substances. 1 mole of carbon dioxide, 1 mole of carbon. And we now have converted from the mass of the compound to the moles of the element. And for some of you, you may really need to cancel your units as you go to ensure greater success. Now we can get to the mass of the element. If we were asked for the mass of carbon, we would have it at this point. They didn't ask for it, so we don't really need to stop there. Rather, we can go after the percent of carbon. We want to know the percent of carbon in this compound. If I have the mass of the carbon after all of this manipulation, what will I divide this by in an effort to get percent?
0.1204.
You got it. The mass of the carboxylic acid. So we're going to divide this by the mass of that sample. Because you want to get the percent of the carbon in that carboxylic acid in an effort to determine its empirical formula. And then to get the percent, you're going to multiply by 100. Did that make sense, Chris? Yeah. Okay. I like to just multiply, numerator, divide, and then divide. But whatever rocks your world, as long as you're doing it correctly, is fine with me. Some of you are a little bit messy with your setup. Watch your sig figs as well. You were given 4. Give me back 4. And you also divided by 4 here. So that's going to be 48.66% carbon. That's the first piece of the puzzle.
How come we start with carbon and not hydrogen?
You could have done the water to get the percent of H if you wanted to. It doesn't matter. That had an additional trick in it. I also just went from left to right. Just do something consistent.
We just avoid the most common.
Right. All right, so now to get the percent of hydrogen, I'm going to start with the mass of the water. I'm going to work it grossly similarly, and I've got 0.0884 grams of water. For every 1 mole of water, I have 18.016 grams of water. And here's where the first tricky piece comes in, and that's the only reason I didn't start. I started with CO2 just because I was trying to work from left to right to just be organized. For every 1 mole of water, how many moles of H? 2 is correct. Be careful there. These problems are very easy to do if you practice enough and you don't make a mistake. If you make a mistake early, it's going to really spiral out of control. For every 1 mole of H, I have 1.008 grams of H. You just want the element. Don't get into, oh my gosh, it's diatomic. Don't go there. And then you're going to divide all of that by the sample in an effort to get the percent of hydrogen in this particular carboxylic acid.
You get 8.212 or 8.218. Do you still have to do it at 4 sig?
No, here you have 3 sig figs, so you want 3. So 8.22%. Sound good?
If you did have 4, do you take the percent? Like, did you have 8.228?
If you had 4 sig figs, you'd have 8.216.
For the first percentage, if you get like, I got 49.17. Is that like completely wrong?
No.
It's okay.
I just hope it doesn't throw things in the long run. You'll see how this really strings. So see if you have what I have and just check your math again.
I did it twice. Yeah, I'm just going out
Okay.
49.17.
I'll take a look with you.
Okay.
All right. We have the carbon. We have the hydrogen. We need to get the oxygen. How can we determine the percent oxygen? Katie. You got it. So it's going to be 100% minus the sum of the 2 we found. Because to get the oxygen, otherwise you'd have to do both of these for it and put them together. It's way too much work.
Percent.
Oh, okay.
When she writes 0, usually she puts a line through it if it's next to it.
Yeah, thanks. Got it. I'm right on.
Now we have all our percents, and you already know how to get the empirical formula from the percent. Let's work through it. I just want to point a few things out that I noticed in the quiz. Most of you were highly successful with this problem. What we had here is 48.66. We can make that grams of carbon. 8.22 grams of hydrogen. 43.12 grams of oxygen. You're going to divide that by the molar mass, and some of you made a mistake right here in your quiz, and unfortunately it made a big mess. Make sure you're comfortable with a mass to mole conversion. If you need to write out 1 mole of carbon over 12.01 grams of carbon to do it, that's fine. However you need to do it to be successful. but where some of you also just had a little hiccup, not a major one, is you're very unclear on your units. When you do this division, you get moles. You can only compare substances with moles, so you may have lost a point there.
If you like do something like that on a quiz, but then you get the right answer at the end, do you still take points off?
I won't touch it on your big quiz because it's certain steps are just worth a point. It's all or nothing. This is one quiz where it is very difficult to follow a mistake through because when things go wrong up here, they're probably going to go wrong here. But you do typically follow mistakes through. Like if you have the wrong limiting reagent, you'll lose the point there, but they'll follow through on what you picked. Here was the other problem I saw in the quiz. So again, this is moles. What do you do next?
But it's not a quantity.
Right, it's just the number. I didn't take off for that, but some of you didn't do that.
So at this point, we're just gonna follow the steps that we did in the last lesson for the empirical formula.
You got it. So 4.052 divided by 2.695, and that's going to be 1.504 moles of carbon. I think this one's relatively straightforward.
Times 2.
And you're going to multiply each of these by 2. Some of you didn't do that either. Be careful.
Oh, I ended up actually doing the fucking gas.
All right, and some of the kids did ask this question too. I want to make this clear. When you multiply, typically, if you're within 0.05, you're good to go. You've got a whole number. Sometimes they'll say if you're within 0.1. And on your next quiz, unfortunately, it did come out 0.1. So I wrote on the quiz, if you've got 0.1 or within 0.1, you're good to go. But typically it's 0.5. So once you have that, what's your empirical formula? All right, and I'm going to write that here. I like to work from top to bottom, left to right, but I want to just get this on the page here. That's your empirical formula.
You want us to balance the equation after that or not?
Hang on, hang on. So you should be good here. The other pieces you should be very comfortable with, but I do want to go over the balancing of this equation because there are some tricks that you may or may not have learned in honors. So what you're looking at here is we've got an empirical formula of C3H6O2. The molecular mass is given at 222 grams per mole. We want to know the molecular formula. Just like you did on the quiz, you're going to go after your empirical formula mass. You've got 3 times 12 is 36, plus 6 is 42 plus 32 is 74 grams per mole. Sometimes you have to do stuff without a calculator, so be careful. Your N, we know, is the molecular mass that was given over the empirical formula mass that you calculated for an N of 3. So what is the molecular formula? C9H, that's bad math, 18, careful, oopsie. 2 times 3 is? 6. All right?
Wait, can you do the 74 part again?
3 times 12 plus 6 times 1 plus 2 times 16. Just using mass numbers, it's easier.
Oh.
All right? Probably nothing. Write the balanced chemical equation showing combustion of this compound. Listen, listen, listen. You're going to use the molecular formula. You're going to use the molecular formula. You're going to use the molecular formula. Go back to your initial equation, and that's why we wrote it out at the beginning, and also to put information under it. With your balancing, when you balance these combustion reactions, they can be a little tricky because the O's are all over the place. You've got 9 carbon, 9 carbon. You have 18 hydrogen, you have 18 hydrogen. Now you got to be careful. You've got 18 O's here, plus 9 O's here is 27 O's on the right. You've got 6 here. I'm going to subtract 6 is 21 O's. What fraction times 2 is equal to 21?
10.5.
Fraction.
That's not.
21 over 2. The big number over the 2. But when you balance your equations, you need the simplest whole number ratio. So we're going to multiply each of these by 2. That's going to make 2. Don't forget this first one. That's the common boo-boo. 21, 18, and 18. And you may want to recheck your numbers to be sure that you are in fact balanced. 18 carbons, both sides. 36 hydrogen, both sides. The O's are tricky. 2 times 6 is 12, plus 42 is 54. 18 times 3 is 54. And we're good to go. All right? Not so bad. You've got to be neat and meticulous. Be very, very careful there. All right? I want to do one more problem with you. You'll do more of it than I will. But I want to make sure you're very, very clear in the setup of this next piece. It's a little trickier. Be meticulous and you'll be successful with it. In the second problem, it says dimethylhydrazine is a CHN compound, and I wrote your quiz similarly where I told you what elements comprise the compound, so there was no wiggle room for error. When burned completely in excess oxygen gas, a 0.312 gram sample produces 0.458 grams of CO2. So that sample is used to determine the mass of CO2. that mass of CO2 will determine the percent of what element?
C.
C. Then the nitrogen content of a separate 0.525 gram sample is converted to 0.244 grams of nitrogen gas. You have two samples. Let's be very meticulous in our setup, and you'll see that this one is also very straightforward to solve. So again, we've got our skeleton, if you will, CX, HY, NZ, plus O2. Again, you're going to get CO2, water, products of a combustion reaction, but because you have a nitrogen derivative of that hydrocarbon, you're going to have a nitrogen containing product. In this case, it's nitrogen gas. It can be ammonia as well, NH3.
How do you know which it is?
It tells you. You don't have to worry about O because it's not in the compound. Now you could have a compound with 4 of them, but if you have 4 of them, they'll probably give you the mass of one of those elements or the percent to make life easier. In terms of the information provided, what you've got here is the 0.312 gram sample yields 0.458 grams of CO2. The other sample is 0.525 grams, and that's going to yield 0.244 grams of nitrogen gas.
So you have to do the same thing with each twice.
In different pieces. So, Tyler, what do you think you're going to use the CO2 for?
Fire carbon.
You got it. So the mass of carbon dioxide will drive the percent of carbon. You try and do that. We'll do it. Hang on, there's a couple tricks I want to show you in the next one. I know you can probably do the whole thing yourself already, but I just want to really point out the second piece. So see if you got the percent of carbon correct. Yeah.
Wait. Oh, okay, I see what
The next piece is a little trickier. I know some of you probably already started it, and that's great because you're already figured out the whole thing. We're going to use the mass of the nitrogen gas to get the percent of what? Nitrogen. But there's two tricks here. In the first one, be careful, diatomic. Here's the first trick coming up. It's not really a trick, but it's the place kids do get tripped up. For every 1 mole of nitrogen gas, how many moles of N do you have?
2.
So be careful on that. And what will you divide this whole piece by?
0.525.
What's in blue? And that's why I did the other colors, because this drove that. So make sure you divide by the right sample, the correct sample mass. Be careful. So that's the other place where it's easy to make a mistake. Don't make it. And essentially this, and that cancel. And now to find the percent of hydrogen, what are you going to do? You got it. 100% minus the sum of those two.
What about the oxygen?
There is no oxygen in your dimethylhydrazine. If there were 4 in there, and I think I have some examples with 4, I'm sure I do, they'll give you a piece of the puzzle to get it going. I'm pretty sure your practice problem has 4.
There's one like that in the book.
Yeah, there's tons of them.
14.4.
All right. You have all the percents. You know how to do the rest. I want you to give it a shot. Initially, this will be very slow for you, but before game day, you have to be able to do this whole problem in 15 minutes. That's the goal. You've got to work on your timing this year. It's going to be critical, especially for part 2. Keep going.
Is it bad if we use the mass from the other periodic table?
It's not really going to matter. I would familiarize myself with the new one just because that's what you're going to be using, but it's not going to matter. Some of you are good to go.
Wait,
Don't look if you're not ready.
How far are we supposed to be?
You should be able to go to the end, to balancing the equation. And if you're not quite there, don't peek yet.
After that, you're probably gonna ask us to.
That's it.
Then you're gonna give us a problem, like Stoich.
No, that's the whole thing.
Boo, then why is this advanced stoichiometry?
The advanced piece is just the way we converted from the mass of the compound to the percent of the element. It's worth
That's the
40
story.
points. That's your part 2 question.
Oh, I thought the stoichiometry part would come after balancing the equation.
No, the stoichiometry piece was the beginning piece.
No, but I thought like.
Yeah,
it
no,
had
no,
to be
no.
more-
I guess you could keep going with it and say, okay, you have this and, you know, this much of this and this much of this and drive it, but no. It's pretty straightforward. Some of your baby stoichiometry questions are in the multiple choice section without a calculator. Make sure you're doing those practice quizzes without a calculator. Otherwise, you're going to have trouble on that multiple choice. You don't get a calculator for the multiple choice section, just the part 2.
Wait, but on the practice quiz that we did like last night, there were like stoichiometry problems with periodic table stuff.
I'll show you some tricks.
We have to do like
Well,
When in doubt, you can also do it on paper. You learn how to
it's like
multiply.
3rd grade.
Oh my gosh.
oh God, you don't have to.
All right, questions here.
That's on it.
All right, some of you finish up. I highly recommend tonight that you finish up practice quiz 1, 2. See if you can do all of it inside and out. Any questions you have, we can hit tomorrow. Practice quiz 1, 2 is what you picked up right after the quiz. All right. Hopefully, you're comfortable with this advanced stoichiometry and the stoichiometry chapter in general. It all fits into that first big idea that we showed at the beginning. Questions here?